we've briefly talked about unit vectors, and we defined them for the I, j, and k. So these are the base vectors that we use to define using the positive parts of the coordinates axis. But what if we can represent every single vector with its equivalent unit vector? So, and we'll see how that is useful. So I want you to go through this investigation before continuing with the video and the lesson itself. So this would be a good start for unit vectors. So let's say you have two vectors, vector A and a vector U. They have the same direction, they're collinear, and vector U is a unit vector. So it has a magnitude of 1. So what do we do in this case? So they're going the same direction. This just has a magnitude of 1. What are we looking at? So I can then write U as a linear combination of vector A, as a scalar multiple, of vector A. So, but what if I need to find vector U? What does it represent? In order to find vector U, I need to find what lambda will be. Well, let's have a look at what we know previously. We know that if I take the magnitude of vector U, it will be the same as taking the absolute value of lambda and the magnitude of vector A. And then I need to find lambda, so I'm just going to solve for lambda. And that's going to give me the magnitude of U over the magnitude of A. Well, I know the magnitude of U by definition. It's a unit vector, so it has a magnitude of 1. So it's 1 over the magnitude of A. So lambda is actually equal to plus minus 1 over magnitude of A, or if I actually use the formula for magnitude, this is what it's going to be. Unit vector U will have the same direction as A if I'm taking the positive lambda, and it will be the opposite direction if I'm taking a negative. So that's just by definition. So then in general, I'll replace now lambda back into here, and I'm just going to consider the positive one. So I'm going to say that vector U can therefore be defined instead of having too many definitions, instead of having another vector A and so on. So I can combine them all together and say that vector U is basically 1 over the magnitude of A multiplied this. So this is a scalar, keep that in mind, multiplied by the vector A itself, and so on. So why is this special? In 3D, obviously you have 3 components. So what are we doing here? What we're doing is we are creating a different way of writing vector A, but this new vector has a magnitude of 1. It has the same direction as vector A, so it has the same, that's an important part, it has the same direction, but it has a magnitude of 1. Now, why is magnitude of 1 useful? The number 1 is useful for a lot of things. Once you have that base of value of 1, you can then change vector U to have any magnitude possible. So if I wanted vector U to have a magnitude of 3, because this full thing has a magnitude of 1, I'll just multiply it by 3 and I'll end up giving it a magnitude of 3. That's something for you to take and digest a bit more, and hopefully I'll talk about it more as we're doing questions. So again, what we've created is taking vector A but reducing it to having a magnitude of 1, and that could help us transform it into different parallel vectors to A, but with any magnitude we want, because we've started with a magnitude of 1 and we can build up to any magnitude we need. So let's do just a few examples here. So I need the unit vector that has the same direction as the given vector. So what we're trying to achieve is I'm trying to create a parallel vector to V but I want it to be a unit vector. So I want it to have a magnitude of 1. So the way we establish that is first we find the magnitude of v. So that's 5 squared plus negative 12 squared, and that will give me 13. And then I could say that there is a vector, and we tend to write, you'll see on some websites, they tend to write the unit vector with this tiny hat on top. You can use this notation if you need to. So I can now create a vector that's parallel to v. So it will be parallel to v. But in order for this to have a magnitude of 1, I need to multiply it by 1 over the magnitude of v. So this is now a new vector, and I can multiply the scalar. So I can go 5 over 13, negative 12 over 13. I can write it in component form, 5 over 13 I plus minus 12 over 13 j. So what I have done is I've created a vector that's parallel to v, but this has a magnitude of 1. And then you could do the same thing for w, but this time it's just 3 components. The magnitude is 7, and then if I need the unit vector, I'll multiply 1 over 7. So you always take the reciprocal, and then with each component, you can leave it as such, but we tend to write it this way. You can write it in component form, and 6 over 7. Okay. So how can the questions look slightly different? This is an example here. Find all the vectors that are parallel to this and have a magnitude of 5. Well, it's without knowing about unit vectors, this will seem like a long process. However, if I can reduce this A to find just one vector that's parallel to it and has a magnitude of 1, I can then transform it to have a magnitude of 5. So that's the idea behind that. So what we're doing is we are looking into there are 2 ways to go about this. You can use the official kind of formula or go the long route. They will both give you the same answer. So if I go back to the formula for lambda, I know that it's going to be equal to, let's actually define. Let's say I'm trying to create a vector b that's parallel to A, but it has a magnitude of 5. So by writing this, you're already telling me that you're trying to do something that's parallel, and then you want it to have a magnitude of 5. So what we know is that from the formula, that lambda is going to be equal to the magnitude of b over magnitude of A. Now I know what the magnitude of b is going to be. You're trying to make it a 5, so I know that this is going to be a 5, and then I just need the magnitude of A. So 2 squared minus 1 squared, 2 squared, and that's going to give me 3. So I know lambda is going to be 5 over 3, but keep in mind we're taking the plus minus because they didn't say it has to be parallel and the same direction. It just said parallel. So it could be in the positive direction, 5 over 3, or negative direction, 5 over 3. So by having that, I can then go back to my initial equation, and this vector that's going to be parallel and have a magnitude of 5 is just going to be me taking the plus minus 5 over 3 and multiplying it with the vector A. So it means that I could have 10 over 3i minus 5 over 3 j plus 10 over 3k. That's one vector that's parallel to A and has a magnitude of 5, and another one is taking the negative. And we end up with this. So these are all the vectors that I could find that will be parallel to A and have a magnitude of 5.